Hello everyone, welcome to Jigyasa's video tutorial series on BWSim-5G simulator. In this video, we are going to look into the cellular concept, analyze the geometry of cells, and using the simulator, discuss practical issues in the deployment of mobile networks. So with a lot in our hand, let us break down into smaller topics. Let us dial back to the early days of mobile network. The primary goal was to provide coverage to large areas using powerful transmit antenna arrays. Each base station has its own radio footprint, which was called as cell. These networks worked well initially, but as the telecom traffic began to increase, they faced a lot of challenges. The biggest challenge was network overloading. To further contribute to the problem was the scarcity in bandwidth resources. This resulted in a very severe capacity crisis. Instead of relying on larger cells with high power tall antennas, the approach shifted to creating smaller cells with lower transmit power. These smaller cells helped alleviate the crunch in capacity that was experienced during those times. The solution was the introduction of concept known as frequency reuse. In this approach, each cell was allocated a fraction of the total available frequency band. What's crucial here is that the frequency band assigned to one cell could not be used by its neighboring cell. So the frequency was reused but not reused by neighboring cells. Now, the network operators had to strike a balance between the coverage and capacity. This is where a notion of fraction of frequency reuse, known as FFR, comes into play. Say we have a hexagonal cell, the minimum FFR was set at 1 by 7, which means that each cell was allocated a seventh of the available frequency bands. We let us move on further to the geometry of cells. When we are diving into FFR and RF planning, it is crucial to have a solid grasp on what exactly will be the radio footprint of a base station, or which in turn leads to the shape or geometry of a cell. What we have used earlier are omnidirectional antennas. These were the go-to choice for coverage. These antennas cast a circular coverage pattern in the azimuth plane. It's like a signal spreading out evenly in all direction. Technically speaking, this would create a circular shape which can be the shape or cell. But let us keep the argument aside for later elaboration. In the modern networks, things have evolved, and we just saw the advent of AAS, or advanced antenna systems. These systems, while having the remarkable ability to create narrow beams, the beams when swept in all direction have a locus which again is a circle. So it can suffice to say that based on the nature of the antenna, the circular shape can better represent the geometry of a cell. But as elegant as the circular cell geometry may sound, it has a couple of quite intriguing problems. The first one is existence of coverage holes. You have non-overlapping circular cells, and because of this non-overlapping parts, you can notice smaller holes that are being formed between the circles. When the analogy is taken to that of a wireless communication part, the users present in these coverage holes may experience a drop in signal quality or lose connectivity altogether. On the flip side, you can overcome this by making the cells overlap one another. You would have something that resembles a Venn diagram. But in these overlap zones, signals from multiple cells can interfere with each other. This creates a complex environment where managing interference becomes a puzzle of its own. So, while this circular cell geometry is a fundamental concept, it's quite important to be aware of the challenges and therefore consider alternatives for this shape. So, what may be the alternative? Let us consider a rectangle. If rectangles are the cell designated shape of a cell, the major problem that arises is they don't quite approximate a circle. So let us move on to a shape such as hexagon. They offer a balance between the FFR and the shape that's simple for analysis. And the simplicity here refers to the hexagon's ability to approximate a circle. If that is the case, a question may be asked where why don't we go for octagon, nonagon, decagon, and other such polygons? The problem is, while they have a FFR of 1 by 9, they can be more complex for analysis, while they may also contain coverage holes, which we saw earlier is quite a difficult challenge in network planning. Therefore, it was decided that hexagon geometry is a popular choice for cellular network, and because it strikes a balance between a good FFR, that is 1 by 7, and being relatively easier to analysis, making it a practical choice for cellular geometry. Now let us discuss about the relationship between finding the optimal intersite distance and different terrains. For this, we will be changing three different terrains: rural macro, urban micro, for three different intersite distances, and make certain inferences from the resultant SIR SINR behavior. Now that we have run three different intersite distances for one terrain, let us make some initial inferences. Let me filter out the CDF separately and the SINRs. From this graph, we can notice that as the intersite distance increases, the performance based on SIR, SINR decreases. From the video on interference, I would like to repeat again that the SINR is the ratio of signal power to the sum of interference plus noise power. So when you increase the size of the cell, the user equipments farther away from the BS experience lesser power and thereby causing this behavior. Where this experiment differs is we will further proceed to plot the same intersite distances for another terrain, that is the urban macro terrain. Okay, since I don't want to clutter up the graph anymore, let us restrict the scope of this argument to a rural macro and urban macro scenario. You could focus on the screen. There are six different graphs, three SANR for urban and three SANR for rural. These are the three SANR for rural scenario, and these three are for urban scenario. So visually, one could understand that the difference in SINR behavior is more pronounced in urban scenario than in the rural scenario. The optimal ISD in a rural scenario could be the larger one, considering the fact there isn't much pronounced difference between the larger and smaller ISD. This is because the propagation characteristics are much more favorable. The path loss is lower and the interference is less complex due to the lower building structure heights with abundance availability of LOS propagation scenarios. When we move to the UMA, there is a stark contrast with its high-rise buildings, densely populated high-rise buildings and then LOS conditions. In these cases, a smaller ISD is more effective. This allows for better frequency reuse, better coverage in urban canyons, and improved overall network performance. And so we conclude this observation and move on to the next one. The next topic of discussion is optimal ISD for differing terrain, minimum distance between the user equipment and base station. The primary question one may face is how exactly can this be configured in the BWSim-5G? This can be done by changing the minimum distance parameter present in the system parameters option. Initially, to show the geometrical change that happens while changing the minimum distance, we will take a much smaller UE and BS and check the layouts. Now remember, this is the layout for the cell where the minimum distance is 10. Now let me clear this and let us increase the minimum distance to 100. So in this, if you can see, when you increase the minimum distance between UE and base station, the user equipments get denser more towards the cell edge. This experiment, we are going to change the minimum distance for different ISDs and observe the behavior change in SIR and SINR. Okay. Now, as done earlier, we filter out the CDF and let us focus on the SINR. Let me zoom inside to, we can see that when the daemon increases, the performance deteriorates. So what does this mean? As we saw earlier through the layout, as the daemon increases, the number of user equipments pushed towards the edge of the cell increases. That is, the user equipments become more dense towards the cell edge. There are two problems to it. One is the increase in path loss. This can decrease the signal power. Mathematically, this can decrease the numerator term present in SINR. Furthermore, it can increase the interference power. Mathematically, this can increase the denominator present in the SINR expression. Both of these are undesirable. Therefore, we have a behavior where as we increase the minimum distance between the user equipment and base station, the SINR performance deteriorates. Again, we will be further expanding this observation by incorporating another ISD, that is 500. Okay, now let us filter out the SINR results alone to make a more nuanced. So if you can see over here, these are the SINR for ISD of 200. These two. These are for SINR of ISD 500 and these are the SINR curves for ISD 1732. Visually, it can be observed that as the cell ISD increases, the impact of dmin on SINR decreases, because when you increase the dmin, you are nearer to cell edge than in a larger cell. Let us keep it this way. When you have a dmin of 100, the user equipment will be closer to the cell edge in a smaller cell than in a larger cell. This is the reason why the following behavior can be observed. Furthermore, the experiments here are restricted to a lesser number of observations for the sake of clearly understanding the graphs. To get a more detailed and exhaustive observations, kindly look into the manual. I'll meet you again with another experiment and its implementation on BWSim-5G with another video. For any doubts, you can contact the Jigyasa team for clarification.